Hello students, today we are going to study measurement of the straightness, flatness and roughness. To start with the surface roughness, we'll first understand what do you mean by the surface roughness. Surface roughness often shortens or the roughness is a component of the structures. Any engineering component processed by casting, forging, drawing, welding or stamping etc. may not have equally finished surface. It is quantified by the deviation in the direction of the normal vector or a real surface from its ideal form. If these deviations are larger, the surface is rough, and if they are small, the surface is smooth. Now we'll see the different element of surface roughness. Starting with the first, surface. Surface of the part is confined by the boundaries which separates the part from any part, substance or space. Next is the profile. Profile is defined as the counter of any section through a surface. Next, actual surface. This refers to the surface of a part which is actually obtained after a manufacturing process. It may be any type of a manufacturing process. Nominal surface. A nominal surface is the theoretical, geometrically perfect surface which does not exist in practice, but in any average of the irregularities that are superimposed on it. Center line. Center line of a profile is the line parallel to the general direction of the profile, for which the area embraced by the profile above and below the lines are equal. The figure on the bottom right will show you a profile of surface irregularities, which will show the center line, actual surface, nominal surface and profile height. Mean line. Mean line of the profile is the line having the form of geometrical profile and dividing the effective profile so that within the sampling length, the sum of squares of distance between the effective points and the mean line is minimum. When the waveform is repetitive, the mean line and the center line are equivalent. Now we'll see the direction of lay. Direction of lay is a predominant direction or pattern of the surface textures. Roughness. Roughness refers to the relatively finely spaced irregularities such as might be produced by the action of the cutting tool or the marks of the cutting tool. Roughness height. This is rated as the arithmetic average deviation expressed in micro-inch or micrometers normally to the imaginary center line running through the roughness profile. Roughness width. Roughness width is the distance parallel to the normal surface between the successive peak or ridges that constitutes the predominant pattern of the roughness. Roughness width cutoff. It is also called as the sampling length. This is the maximum width of the surface irregularities that is included in the measurement of the roughness height. This is always greater than the roughness width and is rated in inch or centimeter. Waviness. Waviness consists of those surface irregularities which are of greater spacing than roughness and is occur in form of waves. It may be caused by the vibrations, machines or work deflections, wrapping, etc. Waviness width. It is the distance between the successive wave peak or successive wave valley. Waviness height. It is the distance from wave peak to valley. Flaws. Flaws are also called as the defects. Flaws are the surface irregularities or imperfections which are occurring at infrequent intervals at a random intervals. Such imperfections are scratches, holes, cracks, pits, cheeks, porosity, etc. Now we'll see the different ways for evaluation of surface roughness. There can be many ways through which the surface roughness can be plotted. Few of these most popular methods of surface roughness plot interpretation are as follows. The first one, most widely used, is the root mean square value, which is also called as the RMS value. Second, center line average method, CLA, or arithmetic mean deviation. It is denoted by RA. Third one is the maximum peak to valley height, denoted by RT or Rmax. And the last one is the average of the 5 highest peak and 5 deepest valley in the sample, denoted by the RZ. Now we'll see the first method known as the root mean square value, RMS value. The procedure to plot the RMS value is as such. First, the center line is located such that the sum of all the areas above the line is equal to the areas below the line. The distance above the center line are taken as positive and below is taken as the negative. The n measurements are made, whether it may be plus or minus, from the center line vertically to the point on the profile and are called as y to the base I. Root mean square value is the positive square root of the arithmetic of all the values of the squares of the values in the set. We'll see the formula. RMS value is equal to under root y1 square plus y2 square plus y3 square plus yn square divided by n, where y to the base I is the profile deviation. Next is the center line CLA or arithmetic mean deviations RA. In this method, the surface roughness is measured as the average deviations from the nominal surface or center line. The arithmetic average or centerline average is defined as the average values of the ordinates from the center line. The algebraic sign of the ordinate are not being considered here. The third method is maximum peak to valley height, Rmax or RT. This is the parameter which is simplest to be determined from the graph of the profile. However, this does not give complete characteristics of the given surface. This parameter is, however, important when the roughness is to be removed, for example, by polishing to increase the fatigue resistance of the work. Here, RP is taken as the highest peak of the mean line, RV deepest valley below the mean line, and to calculate the Rmax, the distance between the highest peak to the deepest valley, Rmax is equal to RP plus RV. Now moving towards the last method for evaluation of the surface roughness, it is called as the average peak to the valley height and denoted by the RZ. This parameter is easier to obtain from a profile graph than the RA. This is the average difference between the 5 highest peak and the 5 deepest valley within the sampling length and measured from a line drawn parallel to the general direction of the profile. This line does not cross the profile. If you see the figure, it is having the 5 tallest peak R1, R3, R5, R7 and R9, whereas it is having the 5 deepest valleys such as the R2, R4, R6, R8 and R10. Now to calculate the average peak, we are having the formula as Rz is equal to 1/5 in bracket R1 plus R3 plus R5 plus R7 plus R line, which are the tallest peak, minus R2 plus R4 plus R6 plus R8 plus R10, which are the 5 deepest valleys. Now moving towards the important part of this topic is how this surface roughness is being measured. The surface roughness can be measured by using any of the following process. It may be a straight edge, surface gauge, optical flat or profilometer. First we'll see the straight edge. It is a tool with a straight edge used for drawing straight lines or checking their straightness. They are used in the automobile sector or services and machining industries to check the flatness of the machine mating surface. A pair of straight edge called as the winding stick are used in woodworking to amplify twist in piece of the wood. It is the simplest type of a device used to measure the surface roughness, but it is not more accurate. Next instrument is called as the surface gauge. A surface gauge is an instrument which is provided with the attachment of a scraper which is used to measure the profile of heights of the surface. The attached scraper helps to mark out the surface profile with respect to the reference line. Now the next more accurate method to measure the surface roughness is the optical flat. It is an optical grade piece of glass lapped and polished to be extremely flat on one or both sides, usually within a few tenths of nanometers. They are used with a monochromatic light to determine the flatness, surface accuracy of other surfaces. Now how does it works? We'll see the working of the optical flat. When an optical flat is placed on another surface and illuminated, the light waves reflect off both the bottom surface of the flat and the surface on which it rests. This causes a phenomenon similar to thin film interference. The reflected wave interfere, creating a pattern of interference fringe visible as dark and light bands. The spacing between the fringe is smaller where the gap is changing more rapidly, indicating a departure from the flatness in one of the two surfaces. Now we'll see how the results of this optical flat are being interpreted. Straight, parallel and evenly spaced interference fringe indicating that the work surface flatness is equal to or higher than that of the reference surface. Two adjacent fringes indicates a difference in evaluation of 1/2 wavelength of the light used. So, by countering the fringes, differences evaluation of the surface can be measured to a better than 1 micrometer. The next measuring instrument is a profilometer. A profilometer is a measuring instrument used to measure a surface profile in order to quantify its roughness. There are basically two types of the profilometer, contact profilometer and non-contact profilometer. Now we'll study the first type of the profilometer known as the contact profilometer. It is also called as the surface roughness tester. A diamond stylus is moved vertically in contact with the sample and then moved laterally across the sample for a specified distance and specified contact force. The height position of the diamond stylus generates an analog signal which is converted into digital signal, stored, analyzed and finally been displayed on the display unit. It can measure a small vertical features ranging in height from 10 nanometer to 1 millimeter. The next type of the profilometer is the non-contact profilometer. An optical profilometer is a non-contact method for providing much of the same information such as that of the stylus-based profilometer. It generally uses light instead of a physical probe or a stylus. Surface texture is measured by optically scanning a surface with a light or a laser. Optical or light-based instrument may also use triangulation or interferometry to measure or capture a surface profile. Although most profile or surface profile provides only a two-dimensional 2D or line file, some instrument can also provide the three-dimensional or aerial topography measurement.